Today I'll be going through the condition for destructive interference in diffraction. So what we have here is we have a big slit. If you don't know what the difference between a big slit and a small slit is, please review my previous uh, video. This is supposed to be slit. It looks like something else, but okay. So we have a big slit over here, and when we have a big slit, it means that we have a continuum of point sources. Okay, this is very distinct, very different from if you have a small single slit. Right now we have a big single slit, so there's a continuum of sources. In a small single slit, we have one source. But okay, so light comes through, and then all these slits, all these point sources would emanate their own light ray and hit a screen. And depending on the angle that they differ from the horizontal, they might destructively or constructively interfere. So today we'll explore the destructive interference of this single slit diffraction, big single slit diffraction. So the condition for destructive interference is d sine theta equals to n lambda, where n is an integer. But so we'll derive this formula today. So first of all, a small comment is, if you want the intensity, if you want to derive the entire intensity pattern, you can do an integration, and then you can actually recover this destructive interference condition. But we'll be using a more heuristic approach, where we do not find the entire intensity pattern, but rather we'll find an explanation for why this is the destructive interference condition. So do note that this is the by the logic of our argument. If we follow the argument later, this means if d sine theta equals to n lambda, then destructive interference. But it does not mean that if not this, then that implies not destructive. Yeah, so at least that's the flow of the logic. Yeah, so do note that it's a if P then Q, but if not P, it does not mean if not Q. So yeah, hope that's clear. So this is a condition, and this is a condition that is sufficient, but it might not necessarily be necessary. So without further ado, let's go ahead. So we have a let's split the slit into two first. Okay, so we split the slit of width d. Oh, sorry, I did not define d just now. D is the distance, the width of the slit. So we split it into two parts, d, so there'll be d over 2 and d over 2. And what we do is we do a pairing. Okay, we'll pair the light ray, we'll pair the source here with the source here, and then we'll pair a source here with the source here. Basically, we'll pair a source at x equals to alpha with, we'll pair the source at x equals to alpha with x equals to alpha plus d over 2. What this means is that so this pairing will then later impose a condition to say that if this source destructively interferes with this source, then they effectively cancel each other out, right? And once they cancel each other out, if we do this pairing for all the sources, then if this entire top section destructively interferes with the entire bottom section, because we form the pairing, then that means there's all the light, when they all add together, they all destructively interfere. So what is this condition for destructive interference in this particular pairing? So the condition is then, one such condition is then d over 2 sine theta is equals to half lambda, right? There's a reason why I didn't put n plus half lambda. You'll see that, so what, I didn't put n plus half lambda, which means that if this condition is satisfied, then it will destructively interfere. But it does not mean that if this condition is not satisfied, then it will not destructively interfere. So this is one of the sufficient conditions for destructive interference of this pairing of sources. So let me just review what we have so far. So what we have done is we have paired each source, we have divided the slit into two, and we've divided it in more pieces later. We've divided the slit into two, and then we've paired the yellow source with the yellow source, the green source with the green source, and so on, such that alpha is paired with alpha plus d over 2. And that means that the entire top half of this slit is paired with the entire bottom half of this slit. And we then say, what if each of these pairs destructively interferes each other? Then you can see that if each of these pairs destructively interfere with each other, then the entire slit would destructively interfere to result in, then the entire slit will destructively interfere with itself, right? Yeah. So, and what is that condition for destructive interference? Pairwise, it is this condition. And if we rewrite it, we get d sine theta equals to lambda. So this is a condition for destructive interference. So this is one of the conditions. So if 1, then we get destructive interference. Okay, so this is 1, d sine theta equals to lambda. But what is another pairing that we can possibly do? Another pairing that can possibly do is we split the slit up into 4 pieces. So we split it up into 4 pieces. Oops, sorry, I drew badly. We split the slit up into 4 pieces. So there goes. Yep. And then we pair this guy with this guy. We pair this guy with this guy. We pair this guy with this guy. Basically, we pair every point source here with every point source here. The same translation by d over 4. And then we pair every point source here with every point source here in the same manner. Similar to the d over 2 case, but this time we do it with a translation of d over 4. So then we say one way for this entire big slit to destructively interfere to result in no light is that every pairing that we have formed destructively interferes with each other. So what is the condition for that? The condition for that is d over 4 sine theta equals to half lambda, right? So what we have here is the yellow one emanates one, both the yellow emanates and then it's an angle theta. Then we'll see that so this is now d over 4 between the two yellow slits. Maybe I draw in yellow. So this is a zoomed in picture of the yellow slits, and then basically this distance is d over 4 sine theta, and for destructive interference is half lambda. So then this results in d sine theta equals to 2 lambda, correct? So this is the condition. This is one of the conditions for destructive interference. So it means that if 2, then destructive. Now this is a condition we can add on to. So we have now two possible sufficient conditions for destructive interference. One is this, and the other one is this. Now we can similarly repeat the argument for 6, but for the sake of brevity and generalization, I will not do the case for 6 completely. I'll just say, so because the case for 6 is d over 3 sine theta, sorry, d over 6 sine theta equals to half lambda, right? And that will lead to d sine theta equals to 3 lambda. And likewise, if we split it up into 2n, we split it up into 2n parts such that each width is d over 2n, then d over 2n sine theta equals to half lambda is the condition for pairwise destructive interference. And what do we get? So we get d sine theta equals to n lambda. And note what n can vary. We start off with n equals to 1, where we split into 2. slits. We split into two, the big slit into two pieces, and we went on to n equals to 2, n equals to 3. So basically n is in the integers or natural numbers. Yeah. So this overall, if d sine theta equals to n lambda for some n in z, then destructive interference. And do note that this is the flow of logic. So if this condition, then at least in our derivation, if this condition, then it leads to destructive interference. It does not go the other way. So yeah, that's the flow of logic in our argument. So if you want to possibly find all the destructive interference, guarantee that you find all the destructive interference, then you need to probably do the integration. But this is a heuristic argument that we have managed to derive by pairing up point sources in the continuum of point sources. So by pairing it up in a smart way, we've managed to find certain conditions for destructive interference. And that is all I have for today. Thank you very much.